And now we're going to think about matchings in general graphs. And so we just need a simple definition. Okay, so last time we looked for matchings in a bipartite graph, and we found out whether they were saturated A, so in a sense they were as big as possible or not. And now we want to think about graphs that are not bipartite. Okay. And interestingly enough, it's the number of odd components that are very important here. So an odd component that's just simply a component in a graph that has an odd number of vertices. So is a component with odd number of vertices. Okay. Okay. And we denote the number, so the quantity of odd components in G by this Q of G. All right, this is a parameter for a graph. I give you a graph, Q of G just tells you how many odd components are in that graph. If the graph is connected, Q of G is either 0 or 1. Either the graph has an odd number of vertices and the graph itself is an odd component, or the number of vertices is even and Q of G is 1. If it's disconnected, then Q of G could be practically anything. Okay, so let's look at a couple simple examples here. So, I mean, these are just basically the ones I drew in the notes, but say you have the following graph here. What else do I have? Maybe a 4-cycle, a single edge, and a single vertex. So say this is my graph G, right? And here Q of G appears to be 3, I think, right? A single vertex, that's an odd size component, odd number of vertices. This is an odd component, and this one is 1, 2, 3, 4, 5. This is an odd component as well. Okay, so Q of G is, in that case, pretty simple idea here. Let me draw another one because this will be pretty relevant to what we're doing here. So let's say we have a graph that rather looks like this. This one's a little more complicated, but doesn't matter too much. Say this here. It's a 5-cycle. Maybe another edge like that. Yeah. And then this guy here. Okay, so this graph here, I think Q of this graph is 1. I think this big component here has an odd number. We can check real quick. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. No, okay. So I probably just like missed something in my picture here. Yeah, let's add this here. Okay. So that component, okay, so this Q of G is just 1, like this big odd component, there's like 2 little even components. But actually what I want to think about here is something a little bit different. And what I want to do is set aside this set of vertices here and remove them. So that set of vertices is S. And then I actually want to look at the number of odd components in the graph at G minus S, okay? We've been using notation of this type throughout the class. I never formally defined it, but when I say a graph minus a vertex set, it's just the obvious thing. It's remove the vertices, look at the resulting graph, all right? Even though like this notation is completely unjustified, right? G is a graph, it's not a set, and S is a set of vertices, like there's no, you know, and moreover, the minus sign isn't even set minus, right? It's some minus sign, although interestingly, in graph theory, we prefer the minus sign to set minus, and it just, like, it means what it's supposed to mean, right? Like most of the time, so we use the plus sign similarly, okay? So in this graph, in G minus S, we have to look at the components, right? So this thing's a component, right? This edge disappears when I remove S. This single vertex is a component, this is a component, this is a component. This vertex is inside of S, so this guy becomes a component, and then this guy becomes a component. And you can check each of those components, even, odd, odd, odd. So I think I see 3 here as well, right? There's 3 odd components and 2 even components. And so this is actually in the theorem I'm about to state. We're going to be looking at this type of thing here. The number of odd components in, well, the blue stuff forms a subgraph, a particular subgraph that derived from removing a set S here, okay? So we're going to have a condition that may remind you of Hall's condition. Yeah, okay, so the theorem is, and this is Tutt's theorem, an important graph theorist. So a graph G has a perfect matching. Sometimes we call perfect matchings, especially in general graphs, we call them a one factor. That's just another piece of terminology you may see in books. A one factor is a spanning subgraph whose vertices all have degree 1. So, you know, what's a subgraph with whose vertices are all of degree 1? Those are just single isolated edges, because as soon as you have 2 edges coming out of a vertex, you get a degree 2. And spanning means it sees every single vertex of the graph. But that's a perfect matching, right? A perfect matching is a collection of independent edges that see every single vertex of the graph, right? That's what this perfect thing meant. We defined that last time. Okay, so if and only if we have the following, what's called Tut's condition. I'll name it star here. So if and only if the following statement holds. So for every subset, the notes say proper subset, which is fine here. You'll see why, but I'm just going to leave it like this. So every vertex subset, we have the following condition: that the number of odd components in G minus that vertex subset is bounded above by the size of that vertex subset. Okay. This condition's a little bit weird. The one in Hall's condition theorem made a little more sense, right? You grab some vertices on the left side in A, and their big neighborhood needs to be at least as big as the number of vertices I grabbed in the first place. Like that kind of like made sense. It was easy to visualize. This one's weird. This says that when I pull off a set of vertices, I potentially create many or few, I don't know how many odd components, but there better not be more odd components than the size of S here. And we'll check that it's necessary in a second. That's relatively straightforward. That it's sufficient, having this condition to find a perfect matching is not clear at all. And it will continue not to be clear even after we've proved it. It's kind of like complete magic, but nonetheless, it does work, right? So maybe just to look at this example up here, at least for this set S that we chose here, the condition's satisfied, right? We got 3 odd components, and there was 1, 2, 3, 4, 5 vertices in the red set. So it was definitely satisfied. 3 is at most 5. But it needs to be satisfied for every single set of vertices in the graph. Okay, so maybe we can make like one just little easy observation immediately here, that there's like 2 cases that are kind of some interest. But let's look at the one when S is the empty set, what that claims. So if S is the empty set, then suppose star is satisfied. It means that it's satisfied for the empty set, and this means that the number of odd components in G, right, G minus S, is at most 0, the size of S there, okay? So for S, we have this guy here, and this implies something interesting about the graph. This says no odd components of G. So every component of G is of even size, right? So all components of even size. What does that say about the number of vertices of G? Every single component, maybe there's only one component, but every single component has an even number of vertices in it. Then the total number of vertices is what? It's even. Yeah, I can read your lips, Eric. This is actually, it's kind of like funny. We can I think you said even, right? So it's even. Max said it in the chat as well. So this is a good thing, right? If we want to have a perfect matching, we better have an even number of vertices, right? If you have an odd number of vertices, you're not going to find edges that eat up all the vertices, because an edge takes 2 endpoint vertices at first. So, okay, this doesn't prove anything, but like, there's this like bonus. Like ordinarily, when you want to prove a theorem about whether or not you have a perfect matching, a reasonable starting assumption would be, hey, the number of vertices better be even, otherwise we have no chance. But like, this is really cool that condition is actually included in the star thing here. That's exactly the case. S is the empty set. That provides you with the fact that the number of vertices is even for free. Like it's cute. It kind of comes out nicely. Okay, and that'll actually come up at one point, but I think it's a nice observation to try and figure out what's going on. The other one maybe is when S equals the entire vertex set. Then this says that the number of odd components of the empty set is at most. There's no content to the statement here, right? The graph with all the vertices removed doesn't have any odd components. Moreover, they need to be at most the size of S, which is all the, like, this is instantly satisfied. It doesn't provide us with any information. So often you'll see, you could put like proper here if you want. right? That it doesn't do you any good there. And actually, moreover, like if S is really big, then it seems likely that this will automatically be satisfied as well, because you're not going to have, you'll have fewer vertices left over than S. So even if you have a bunch of odd components, there'll be fewer than this here. But we're not gonna do anything with trying to optimize that. There's no sense in doing it. Okay, so I'm actually going to erase this little bit here because it's not important. But you can say proper if you want. Okay, so let's get to the proof here. So first, I want to show the forward direction, that having a perfect matching implies this condition here, right? That's what I want. Yeah, okay. So if G has a perfect matching, then star holds. Okay, so how do you check star holds? You grab a set S, and then you look at the resulting graph. So we have some components. These are the odd ones, and I'm going to put the even ones down here. Most of the time in this proof, the even components we're not going to be concerned with at all. Like somehow they're not going to be that important, but the odd ones are really going to matter. So these are the odd components. Okay, and these ones are even. And here, what I want to prove is that this quantity, the number of odd components here, of which there are Q, G minus S of them, that there are no more of these than the set S here. Okay. Now, what do we know about the graph? We know that it has a perfect matching. So I'm going to draw, I'm going to do this repeated. Well, it kind of depends. I'm going to draw in blue the edges of the perfect matching. I don't know where they are. Like some edges might be inside of S, some edges might be inside of these even components. Edges also can go between these two things here, right? There's a perfect matching in the original graph. So edges of the perfect matching can be here, can be here, can be here. Like these are all locations possible for edges. They can't go between classes because there's no edges between those classes, because that means these two things would be together as a component, okay? So the blue edges represent where the perfect matched edges might be. I'm going to erase these edges though, because like I don't want to make any assumptions yet. Okay, so now let's think for a second here. Look at just a single odd component real quick. It's possible there are matched edges inside of it, but can all of its vertices be matched by blue edges inside of the component? No, right? Because there's an odd number of vertices here. So like I might have a few blue edges like that, but there's always going to be at least one leftover vertex in there. Where does the blue edge on that vertex have to go? Like there's a vertex inside of there, no matter what, that has a blue edge going where? Yeah, to S, right? There's nowhere, it can't go to another component because those would be combined in a component. So it has to go to S, right? There's definitely one. There might be more, but there's at least one. Okay, so at least one vertex in each component of G minus S with perfect matching edge to S. Okay, so for each odd component, I've got an edge like that type. Is the following picture possible, that they both go to the same endpoint in S? No, the blue edges form a perfect matching. None of the blue edges touch each other, right? So each of these vertices here sends an edge to a unique vertex of S. And that's it. Now that means that the size of S, therefore, the size of S is at least as large as the number of odd components, right? There's a vertex in S for each one of these components. There might be even more, but there's definitely at least one. Okay, so the size of S is greater than or equal to Q of G minus S. Okay, so that proves the forward direction there. That no matter what set of S I choose, I get one of these blue edges. Okay, notice again, even when S is the empty set, that just immediately tells me, oh, there can't be any odd components, because each odd component would send an edge across there. So, but I don't, in this, I just take an arbitrary S. I don't even have to think about what it looks like specifically. Okay, the remainder of the edges of the perfect matching, like I don't know where they are. Like they might be inside of here, they might be inside of here. There could be other blue edges going across, things like that, but I don't care. I'm just looking at these three in this specific picture that guarantee that S has size at least 3. Okay. All right, so that means it's necessary, right? This condition is definitely going to hold if you have a perfect matching. Now, the reverse direction is well, it's not extremely challenging. It's a little bit sort of mystical. But if I have a graph with this condition here, how do I establish that there is a perfect matching here? And this is going to be this sort of annoying proof type where I'm going to assume this condition, and I'm going to assume, for the sake of a contradiction, there's no perfect matching. and my contradiction every time will be finding the existence of a perfect matching, which is irritating because, like I've said before, that suggests that we should be able to just go directly and find the perfect matchings. But you'll see why we can't do that. The proof just requires us to do it in this way. But I at least personally find those proofs the least illuminating, right? Like in some sense, like it doesn't, like, yeah, anyway. Okay. So now let's do the other direction. And a lot of times these come up in like the maximum substructure type proofs, where I take a maximum, edge maximal example or a longest path. Sometimes this type of thing happens. Okay. So now suppose that star Tut's condition holds, and show that there exists a perfect matching. Like we won't find it directly, but okay. So for the sake of a contradiction, someone I'm researching with recently wrote, I've never seen this until like last week, but for the sake of a contradiction, that's shorthand for it, right? Suppose no perfect matching, okay? And find an S that, okay, I'll put in parentheses because that fails star. Right, this is gonna be our first goal here. Is that actually what we're gonna do? Yeah, in this first part we will. Okay, so what's important though is in order to prove this, for the sake of a contradiction, we're just going to suppose there's no perfect matching in G. I'd be proving the contrapositive here. Okay, I actually don't know if I need the parenthesis side. I mean, I don't have to write this at all. Like this is just a goal. It's not part of the proof. But okay, so the first thing I want to do here is I'm going to call this a claim. So we can assume G is edge maximal without a perfect matching. So when you say something's edge maximal, it's under the condition of something else, because otherwise edge maximal just means you're a complete graph. So what I mean here is we've got G and it has no perfect matching, okay? But star holds. I'm going to suppose that I'm going to prove to you that I can suppose that G is edge maximal, which means that it has as many edges as possible, meaning if I add an edge to G, it will then have a perfect matching. Okay, so as soon as I add an edge to this graph G, it's going to get a perfect matching in it here. I'm not going to, I don't weigh in on this condition in the new graph just yet. I'll come to that in just a moment here. Okay, so we can assume it's edge maximal. So that's not exactly clear why we can assume that, because again, if I add edges to the graph until I get to the point where the next edge would add a perfect matching, like that may ruin star. Maybe the resulting graph doesn't satisfy star anymore, or like who knows exactly what happens. Okay, so let's figure out why this is true here. Okay, so why? Well, suppose G is a subgraph of G star, and G star is an edge maximal without a perfect matching. Okay. So G lives inside of G star. So if G is a proper subgraph of G star, then G is not edge maximal. And we'll prove that, like, if we prove it for G star, we get it for G as well. So we could have just assumed that G was G star. Like finding okay, let me just continue with it. Okay, so if we find a set S in the vertex set of G star that fails star, then what does that mean? I'll draw a picture here. This makes this a lot easier. So then we have that set S in this bigger graph G star. So like, I don't know, let's think about, so this is G, and how does G star look like? G is a subgraph of G star, so there's like extra edges in that I add to G to get G star. Okay, so like, then I can say it like this. I think this is the best way to visualize this problem here. And in this case, what edge maximal means, again, is that adding an edge gives you a perfect matching. So there may be multiple different versions of G star, but I can literally arrive at a G star by just adding edges to it until I can't. Like eventually I will reach a graph that is edge maximal without a perfect matching. So just suppose I've done it this way. Like I added edges, they can be incident to each other too. Okay, so what that means is that in G star, this set here fails Tut's condition. So it's not bigger, at least as large as the number of odd components in S, right? That's what it means to fail Tut's condition here. Okay, and what I claim here is that this is going to be bounded above by G minus S. So if I remove that same set in S, then the number of odd components in this graph here is at least as large as the number of odd components here. So finding this bad S in G star was already good enough to find the bad S in G. Okay, I need to prove this though. Like I just wrote it down here. It's not clear that it's true. So for this, let's look at a picture. Okay, so we're looking in G star first, and here's S, and then here's the odd components. I'm not even gonna write the even components, so odd. Let's even make these a little bit bigger. Yeah, I mean, usually when we illustrate these, the like odd components look small, but I don't want to mislead you. The size of the odd components is not what's important. The quantity of the odd components is what's important. Okay, so these are the odd components. And in this case, I know that there are more of them than S. Okay, that's what it means for S to fail Tut's condition. Now, this is in G star. I'm interested in the odd components when I remove S from G, not from G star. Now, remember in this picture here, the difference between G and G star is some added red edges. So there are red edges in this picture here, and where there might be red edges inside of S, those don't have any effect. There might be red edges from S to the even components. That doesn't have any effect either. I mean, it might have an effect, but it's not going to be important. There might be red edges inside of these components. There might be red edges between these components. But what I really care about, like all these edges here across are going to die in G or G star when I remove S, right? It doesn't matter what edges there. But it's the edges inside of these components that matter. Okay? Because now let's compare the two graphs. Let me actually write G star in red. Right, so G star has all of G plus these additional red edges, and G doesn't have the red edges, okay? So in this picture here, this is a picture of G star with S removed. And let's compare it at the same time to G. In G with S removed, I get these blobs, but these things, they may not be components anymore because it's all these vertices of G star, but the red edges are missing as well. So when I take these red edges out, what potentially happens to this component here? It may be smaller components. It may be just the same component, then it's still an odd component, or it might be that in G, after removing the red edges, this actually breaks up into several pieces here. But what can you tell me about the components, the new components? Like I call them new components, but they're actually old components because we started with G, but what can you tell me about the components in that list there? At least one of them is odd in G minus S, the original G minus S. If each of these components that this odd component breaks into is of even size, then the whole thing was even. I didn't destroy vertices, right? One of these components, when I break an odd component into smaller components, at least one of the new components is of odd size, right? You need at least one odd number to add up to an odd number of vertices. And same thing here. Like this one, maybe it's only two components. This was all odd, at least one of them is odd. I mean, in this case, exactly one. But so at least one odd component from that one. And say this one, after removing the red edges, didn't change, then there's still an odd component. So when I look at G minus S, the components out here, there might be a lot more components than before, but for every odd component of G star, there's at least one odd component of G. And so that actually satisfies this inequality here, right? This could be strict. There could be way more odd components, but there's at least one for every odd one. Moreover, the even components down here, they may even end up producing odd components, but that just further helps my cause, right? So I don't need to examine them at all, okay? So this means that Q of G minus S is at least as large as Q of G star minus S, okay? And that's this part here. And so this implies, so S also fails star condition, Tut's condition in G. So what is the implication of this? The implication of this is that we can just assume that G is edge maximal. Because, I mean, the basic reason is the following. If G is not edge maximal, add edges until it is edge maximal, okay? Once it's edge maximal, find this set S somehow. This set S will also fail Tutt's condition in the original G. So like we only need to focus on edge maximal graphs, because if we can find S, a bad S in G star, then we found it in G as well. So just save the trouble and just start with G star. Assume it's edge maximal. Okay. So this means we can assume G is edge maximal. So I won't talk about G star anymore. Okay, edge maximal without a perfect matching. And that'll be crucial. Okay. Because if we can find this set here. And now from now on, we're actually going to be trying to find a perfect matching to get the contradiction. But the point is, here this gave a contradiction in both cases here, because we said that it satisfies star. So if G star doesn't satisfy star, then G doesn't satisfy star. That's a contradiction. Okay. All right. So I should have put that. This was a contradiction. Okay. So that establishes our claim here. All right. Now, yeah. So now what's the next step here? Oh yeah. Okay. So we define something first here. So now we're working with G. So you can forget the preamble now. We're just essentially starting the proof. We just have the bonus that G is edge maximal, which we will absolutely use. Okay. So we're working with G. It's edge maximal. So, okay, I'll just say edge maximal, no perfect matching, and satisfies star. This should be a contradiction. And again, I told the contradiction will be that there is a perfect matching. Actually, that's interesting. At this point, I think we don't need any more to go for a contradiction, maybe. So in order to establish the claim, we did, but okay, I'm going to do this on the fly here. So if we run into trouble, this requires some maturity, all right? We're just going to say that it's edge maximal. Oh, no, sorry. Edge maximal makes no sense without the fact that there's no perfect matching, right? Otherwise, like this does, this doesn't actually make any sense, because I could just make the graph complete and it would satisfy star. Okay, yeah, sorry. So I do need this, and you'll see why in a moment. Okay, so it's an edge maximal perfect matching free graph that satisfies star, and I'd like to have a contradiction here. These graphs shouldn't exist. Okay, so we're going to find a specific S here that's going to work for us to get this contradiction. Okay, so let S be the set of vertices in G that are adjacent to every other vertex in G. Sometimes we call these universal vertices. They're adjacent to everything. And just to be perfectly clear here, they're adjacent to each other as well. So they have degree V of G minus 1. So take all the vertices who send edges to every other vertex of the graph. Let that be S. And we, of course, allow that S is empty, right? Maybe there's no such vertex, but that's going to be our set S, and this is going to be this one's going to work for us, okay? So this is S. I haven't removed it yet, but I know this is the rest of G. This is G minus S, and every vertex here goes to every single vertex across there, and it also goes to the other vertices inside of here. Okay, that's the definition of the vertices in S. They're the vertices of degree n minus 1. Okay. Again, if no such vertex exists, fine. S is the empty set. All right. Okay. So now we have an important claim here, that in this edge maximal graph, the structure of the G minus S is very, very nice. Okay, so the claim is the components of G minus S with this very specific S here, this S that saw everything here, they are complete graphs. Okay, that's our claim. So every component over here, after removing this, is actually like a complete graph, has every single edge possible in it. Okay. So this, I mean, the claim is that this graph looks pretty nice, that I've got S, and then these are the components. Each of these is complete. And moreover, S is adjacent to all the vertices in them as well. There's no, the only place we're missing edges is between the blobs. Okay, so this graph like looks nice. That's the claim, that's the claim. Okay. So let's prove it. So if not, this is the proof of the claim. So if not, then we have the following scenario. Here's S, and one of the components is not complete. Let me make it even bigger. So this is one of the components, and it's not complete. So if it's not complete, it means that there is a pair of vertices that are not adjacent to each other, right? That's the witness for not being complete. But there's something there's something more here. These two vertices are in a component. Okay, so they actually is this clear? Actually, we have to think about this one for a little bit. I claim the existence of the following structure here: a vertex with two neighbors that are not joined to each other. Okay, that's actually the witness for not being complete. If you never have this picture here, then you're either disconnected and not a component, or you're not complete. Okay, so this guy exists. So I'm going to label it X, Y, and Z. The reason for this, if you don't see, like, so the way I started the argument for this is not great. Definitely there's a pair that are not joined by an edge, but I don't know that they have a common neighbor necessarily. There should be a path from X to Z. But if you look at the end of the path or somewhere along the path, you're going to have two vertices along the path, like two vertices separated by a central vertex along the path that are not adjacent to each other. Like that has to happen somewhere, otherwise you're complete. Okay. All right, so we have this configuration. There may be other stuff in this component. We also have one other thing. Y is not adjacent to all the vertices in the graph. Why is Y not adjacent to everything? Why is Y not adjacent to everything? It's a technical matter. I didn't quite catch that, but it's because otherwise it'd be an S, right? S was the vertices that were adjacent to everything. Y is, I put it here, so it's not an S. So that means that there exists a W. It might not be in the same component. It might be, I don't know. But there's a W that's not adjacent to Y, right? Okay. So I'm going to say not complete. So X, Y, Z exist as described, but I don't want to write it out. I just have a picture. And as Y is not in S, there exists a W. Okay. I mean, we argued out these things already, but now my graph has this nice configuration. I've got Y, who's adjacent to X and Z, who are not adjacent to each other, and then Y is not adjacent to W. Okay. And notice that the vertices X and Z are somehow like symmetric as far as these four vertices are concerned here, right? I don't know. I mean, I don't know what X is adjacent to and Z is adjacent to, but they're both adjacent to Y. They may or may not be adjacent to W. I don't weigh in on that. Okay, so now I want to consider the following two graphs. I want to add in the edge, I'm going to put this in red here, XZ. And I also want to consider adding in the edge YW. Those edges are missing, so I could add them back in to create a new graph. Okay, so G plus XZ and G plus YW. These are two graphs with more edges than the original. So what can you tell me about these two graphs here? They both are new graphs that contain one more edge. Yeah, exactly, Eric. They have a perfect matching. Is that what you said? Okay, I can't read lips. Let's suppose you said that, right? So both these graphs here have perfect matchings by edge maximality of G, right? G was the biggest graph of this type that didn't have a perfect matching. If I add an edge to it, I get a perfect matching. So this graph has a perfect matching, and this graph has a perfect matching. Okay, so this one, let's say it has perfect matching M1. I don't know, like I have no idea what it looks like. And this one has perfect matching M2. These two graphs have them. And the perfect matching, the M1 is gonna be in red and M2 is gonna be in blue. Now notice these two perfect matchings are almost perfect matchings of the original graphs, right? Think about this perfect matching, the red one. It uses this edge here, which does not exist in my graph, but all the other edges are edges of the original graph. So every single vertex of G sees a red edge, except for XZ, because that edge isn't actually present, available to use there. So this is almost a perfect matching of G. It just comes up short by one edge. X, Z are not actually matched by it in G because that edge is not present. in G plus XZ, it's a perfect matching, but XZ is not there. And the same thing happens for the blue one. The blue one sees every single vertex except for Y and W, because that edge isn't actually in G. Now, what I'm going to do here is create a perfect matching by somehow mixing the red and blue together in a clever way, okay, in some fashion. And we'll do that in two cases here. And the first one kind of makes it easy to see how this goes. So what I'm going to do is let H be graph created, okay, by the union of M1 and M2. All right. So I've got the red edges, which see every single vertex of the graph, and I've got the blue edges, which see every vertex of the graph. And I'm just going to squeeze all those together. Okay. Now I need to say something important here. This graph is actually potentially a multigraph, right? Because it may be that, like, you know, over somewhere here, like in my graph, maybe in an even component, those two vertices are joined together by a red edge, and they're joined together by a blue edge. So like the same edge is repeated there. That might happen. I don't know. I think maybe you can prove that this doesn't happen, but we're not going to prove that it doesn't happen. We're going to allow that it does happen. Okay. Let's look at what H looks like though. So H is the collection of all the red edges and all the blue edges. It uses the same vertex set as G. The edge set is almost a subset of the edges of G, except it's definitely got, H includes this edge here, and it includes this edge here, which are not a part of G at all. So this actually has two bonus edges, but a lot of other edges have been thrown away, right? In fact, how many edges does H have? It has exactly as many edges as vertices, if you think about it for a moment there, right? It's got, a matching has half as many edges as vertices, and it's got two matchings together, okay? So what does H look like? What are the degrees in H? What are the degrees in H? So H is the union of two perfect matchings. A vertex in a perfect matching has degree 1, right? For each vertex is a red edge coming off and a blue edge coming off. Not two red edges, not two blue edges. You might have this picture here as well, where the red edge goes here and the blue edge goes here, but this vertex here definitely has a red and a blue coming out of it. So all degrees in G are equal to 2. What does a graph look like whose 2 regular? Every single vertex is of degree 2. What does that look like?
Cycle.
Yeah, it's the components are cycles, right? It might be one big cycle or it might be a bunch of small cycles. So it actually looks like the following. Not only is it cycles, what we can say even more about those cycles actually. So degree 2 says everything cycles, but the cycles are pretty in this graph here. All the cycles alternate between red and blue. You can't have two red edges together in a cycle because the red edges don't touch each other. So all the cycles are nice. They look like, okay, I'm gonna have to, this is a little challenging because I'm gonna have to, but every cycle looks like this, right? Now I can't, like, it's odd cycle's not an option here, right? So I've got to actually continue. So every component looks like an even length cycle because it alternates red, blue, red, blue, red, blue, because all the edges were red or blue. You might also have components that look like this, as we discussed. And maybe I'll draw one more here, although. So this is what H looks like. It's a collection of a bunch of even length cycles, which are really nice here. Okay, so now, that's H, that's what it looks like. Okay, now we distinguish two pretty easy cases. I'm gonna try and basically prove these like pictorially and explain. The notes flesh them out maybe more formally, but it's so much easier to see this proof by just like examination, okay? So case 1 is that, case 1 is that XZ, that's an edge, that's actually a red edge, right? And YW are in different components of H. Okay, that's case 1. So keep in mind that the red edges in H include this edge XZ, and the blue edges include this edge YW. And keep in mind, those edges, XZ and YW, do not exist in my original graph. So if I want to form a perfect matching, I want to avoid using those edges if I can. So let's look at the picture then. So they're in different components. So what that means is, I'm gonna draw it here. The component containing xz looks as follows. It's a red edge here, and then let's say it's of length 6, the component, just for simplicity's sake, but it could be of any length. Remember what do components look like? They're alternating cycles here. So it looks something like this. And then let's just draw it like that, but it could be a longer cycle. Okay, so xz is here, and then what's the rest of the graph look like? The rest of the graph still has a bunch of components, but the rest of the graph has a red perfect matching, and at the same time it has a blue perfect matching. Right, that's the rest of the graph. There's no edges across in H. So now what I'm going to do here is take blue edges, sorry guys, edges of this component, and from this one I'm going to take red edges. I claim this is a perfect matching in my graph G. So the blue edges here see every vertex in this component, and crucially, do not use that edge, which is forbidden to use. Now over here, I had either the red or the blue matching to take. Why did I take the red edges instead of the blue ones again here? What's nice about the red edges here?
YW is not one.
Yeah, it avoids YW. YW is blue. So this avoids YW. So now I've found a perfect matching of this graph because all these vertices here have a matched edge and all the vertices here have a matched edge. And I didn't use XZ and I didn't use YW. So that's a perfect matching of the original graph. This is how I mixed the two perfect matchings. Okay? Every single vertex sees a red and a blue edge. So I took the red ones to avoid using YW. And over here, I took the blue ones to avoid using the red one. That's all I needed to do. Now that was crucial that they were in different components. Imagine that XZ was here and YW was here. Then I can't say, oh, take the blue, because that would force me to take YW. And I can't take the red because that would force me to take XZ. So that's why case 1 worked. But case 2 is when they're together. Then I have to come up with some other strategy. Let me erase those because that was not the case here. Okay. So in case 2, is that you have a long cycle here. How to do this? This is one of the components, and XY is in it. Oh, sorry, no, there's no XY. XZ is in it, and YW is in it. Okay? Now, I want to emphasize some things here. So this one's red here, and every other one is red. So red, 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 red. Say it looks like that. The others are blue. Okay? So this picture actually is making an assumption here, but fortunately it's going to be okay. Okay, look, YW is definitely in this cycle here. XZ is in the cycle, but maybe it's ZX, not XZ, right? The orientation of this edge is not like, there's two different ways it could be oriented, right? Like if I travel around Y and reach X, or I travel around Y and I could reach Z instead. Like those are two different potential situations. There's no loss of generality to swap the two here, okay? Either you don't believe that, and then you'll just have to see that the proof I'm going to give here would have worked if they were swapped, or you actually see it from the definition all the way up here of X and Z. From Y's perspective, there's no distinction between X and Z. So like if the two vertices down here appeared in the reverse order, if they were ZX, I can just like rename them so that this one's the X one. I can do that if I want. Okay, so they're in the same component, and then the remainder of the graph here doesn't see either of them. So the nice thing here is that here I can just take the red edges or the blue edges. Like I'm not going to worry about them at all. Somehow I have to figure out how to match this guy up here. Now, As we saw before, if I take all the red edges, then I take xz. If I take all the blue edges, then I take YW. So I can't just do that. But there's a missing edge in this picture here that doesn't exist in H, but does exist in G, right? H was just the red and the blue edges, but G had other edges. G has this edge, and G has this edge, right? Those are actually hiding in the background. Those are edges of G, right? The definition of X and Y, sorry, X and Z was that they were adjacent to Y in the first place. So these two black edges are at my disposal for making a matching. They're not a part of H, but remember, I don't care about a perfect matching of H. I want a perfect matching of G. All the edges of H are in G except for this edge and this edge, right? Those don't actually exist in G, but these two black edges do exist. And now using these two, I can get a perfect matching. Because what I'm going to do now is take, let's see if I can figure this out. Let's take over here, let's take red, red, red. So from Y to X, I'm going to take red edges there. So that matches up. No, I don't want to do that. Sorry. That's the one thing I don't want to do. I'm going to take from Y, don't take the red edge coming out. Take the blue edges. Blue, blue, blue. That will eventually match up with X if I take blue. So take here, take blue. Okay. That'll match up X. It'll leave Y unmatched. I don't use that edge though. I shouldn't use that edge, and I don't use that edge. And then on the other side, I'm going to take the red. So then I take this red, red, red. Take red. From W to Z. Okay? That matches up W, everything in between, and comes up short of matching Z. Right? This is definitely a blue edge here. This is the red edge in between. So everything is matched at this moment except for what? What vertices don't see this part of my matching yet? Let me put this in green. So I take, what did I say? I take blue, blue, blue. And over here I take red, red, red. And the only two vertices remaining unmatched at this moment are Y and Z. So take this edge too. Okay? That, again, was not available to me in H, but does exist in the original graph. And then also here I take the red edges, so those are green. So now the green edges are a perfect matching of G, right? Every single vertex of G, every single green edge is in G, and they form a perfect matching. These ones I got for free, basically, because like all the other components didn't involve the two bad edges, so I could just take whatever was there. And then over here, oh geez, okay. So then I got my perfect matching. We're actually not done with the proof now though. There's one remaining part here, and I'm out of time, but I'll let you guys read it because the last part's kind of fun. So now we have, what's the last step here? So we okay, yeah, right. So let me just tell you in words what the last step is, so you can check it. So this means this was a contradiction. We found a perfect matching. So what did we just prove? We didn't prove the theorem. We proved this claim all the way up here that the components are complete graphs. That's what we actually proved now. Okay, and so now I can hand wave the end of the proof because it's actually very simple, and we've already kind of seen it. So we proved that claim by finding a perfect matching, which was a contradiction, strangely. And now let's look at that same S. These were the vertices adjacent to everything. And let's look at the components here. These are the odd ones. And these ones are the even ones. And I know that each one of these components is a complete graph. So how do I find the perfect matching in this graph? Which again was the ultimate goal at the end, was to actually find a perfect matching. And here we'll find it directly. So now we're not doing a contradictory proof anymore. The contradictory proof was for the two intermediate claims. How do we find it here? Knowing that S is adjacent to everything and these guys are complete, do the following. For each of these odd components, just send it to any random vertex of S. Any random vertex of S, I mean, don't go to the same one. Okay? S is large enough to absorb one green edge for each of these because S satisfies Tutt's condition. Now there's remaining unmatched edges in the graph. The even components, those are easy. Just since it's complete, just match them up however you want. There's a bunch of different ways to match up the vertices in these guys here. Right? Even number of vertices, just choose any pairs of them and do it. These odd components are missing one vertex, so the remaining number of vertices is even, so I can just match these guys up as well, however I want. Again, because they're complete. If they weren't complete, I have to be careful how I do it. Because they're complete, I can do whatever I want. Now, what's the last place I still need to match up edges? S has potentially some other edges, and I'll leave this one as an exercise, In order to do that, I need to know that what's left in S is of even size, right? So like what hasn't been matched yet, is this even? If it is, we're fine, because remember, this is also complete because the vertices of S are adjacent to everything. So if it's even, I can match them up. If it's odd, I can't match them up. But I'll tell you, if it's odd, it means that the graph had an odd number of vertices. You can check. You can check carefully that there's an odd number of vertices in the graph if what's left over here is odd. And we already established that there's not an odd number of vertices in the graph. So that actually finds the perfect matching and completes the proof. And actually, this does suggest an algorithmic way to go about doing this. You need to find these super high degree vertices. Even if it's an empty set, it works. Okay, there's a nice corollary, but I'm going to stop there. I've kept you guys. Yeah, that's the end of the proof there. Tuts is a beauty. Yes, it's a bit mysterious, but I think it's a great one.